This video follows from the first lesson on simple linear regression. If you haven't watched that video yet, I recommend you go back and watch it first. In this video, we'll cover some statistics around sampling, including bias, mean squared error, standard error, residual standard error, R-squared, and sum of squares. Let's talk about bias. When we sample many times from a population, we use sample estimators to estimate the true parameter values. For instance, mu is the true mean of the population, and mu hat is the sample mean, our estimator. Every time we draw a new sample, we get a different mu hat. By calculating mu hat across multiple samples, we create what's called a sampling distribution of mu hat. It tells us how mu hat behaves across repeated sampling. An estimator is considered unbiased if its expected value equals the true parameter value. In other words, mu hat is an unbiased estimator of mu if the expected value of mu hat equals mu. This means that on average, across all possible samples, our estimator hits the target. No systematic overshooting or undershooting. And if this condition does not hold, then the estimator is biased. It consistently misses the mark in one direction. Now let's bring this to linear regression. For beta hat 0 and beta hat 1 to be unbiased estimators of beta 0 and beta 1, the expected values should equal the true values. The expected value of beta hat 0 equals beta 0, and the expected value of beta hat 1 equals beta 1. With some algebra, it can be shown that beta hat 0 and beta hat 1 from ordinary least squares are indeed unbiased estimators of beta 0 and beta 1. But that's beyond the scope of this video. In the video on simple linear regression, we introduced the error term epsilon, which accounts for the deviation of observed values from predicted values from the true model. For simple linear regression, we can write that error explicitly. Epsilon sub I equals y sub I minus the quantity beta 0 plus beta 1 times x sub I. This is the true error, and it is unobservable because we never actually know the true values of beta 0 and beta 1. The variance of the error, sigma squared, measures how much observed values deviate from true values due to random noise. But how do we estimate this variance if it's not directly measurable? One common method to estimate this variance is through the mean squared error, or MSE. The residual, E sub I, or less commonly written as epsilon hat sub I, is the estimated error based on the fitted model. Unlike the true error, residuals are observable because they use the estimated coefficients that we actually compute. So to obtain an unbiased estimator of sigma squared, we define the mean squared error, MSE, also written as S squared or sigma hat squared, as 1 over n minus 2 times the sum of the squared residuals, which is the same as RSS divided by n minus 2. Here, n is the number of observations, and 2 is the number of parameters we estimated, namely beta 0 and beta 1. Without this degrees of freedom adjustment, the estimate would tend to be too low, meaning it would be biased. With this adjustment, the MSE is an unbiased estimator of sigma squared. It follows that the residual standard error, RSE, is simply the square root of MSE. We can also write it as S, or sigma hat, or equivalently, the square root of RSS over n minus 2. And the takeaway here is straightforward. A smaller RSE indicates a better fit. Now that we have the mean squared error in our toolkit, let's talk about something that builds directly on it, the standard error. The standard error, often abbreviated SE, measures the variability of an estimator from the true parameter value. It helps us understand how much our estimate would vary if we repeated the entire sampling process many times. A small standard error means our estimate is reliably close to the truth. For the coefficients in a simple linear regression model, the standard errors tell us how precisely we've estimated beta hat 0 and beta hat 1. Let's start with the standard error of beta hat 0, the intercept. SE of beta hat 0 equals the square root of MSE times the quantity 1 over n plus x bar squared over the sum of xi minus x bar all squared. Let's break down the ingredients. MSE is our unbiased estimate of the variance of the error term. N is the sample size, x bar is the mean of the predictor variable, and the denominator inside the parentheses is the sum of squared deviations of x from its mean. Now for the slope. The standard error of beta hat 1 equals the square root of MSE divided by the sum of xi minus x bar squared. Equivalently, it can be written as RSE divided by s sub x times the square root of n minus 1. Here, s sub x is the sample standard deviation of x, defined as s sub x squared equals 1 over n minus 1 times the sum of xi minus x bar squared. Looking at the formula, two things drive the standard error down. First, a larger sample size n. More data, more precision. Second, a larger spread of the x values. When your predictor covers a wider range, the slope is easier to estimate precisely. That's the standard error for simple linear regression. It tells us how much our coefficient estimates would vary across different samples. These formulas will come back when we build confidence intervals and hypothesis tests. In this section, we introduce r squared, the coefficient of determination. Recall that RSE equals the square root of RSS over n minus 2. It gives us an estimate of the standard deviation of the error term. Useful, but it's measured in the same units as the dependent variable, which makes it hard to interpret on its own. It would be nice to have a standardized, dimensionless measure of the model's fit. Enter the r squared statistic. This statistic measures the proportion of variance in y that is explained from x. In terms of formulas, r squared equals the total sum of squares minus the residual sum of squares divided by the total sum of squares, which is the same as 1 minus RSS over TSS, or equivalently, regression sum of squares divided by TSS. In other words, r squared tells us what fraction of the total variation in our data is explained by the model. The rest is unexplained. Let's break down each component. TSS, the total sum of squares, represents the total variation in y around its mean. TSS equals the sum of y sub I minus y bar quantity squared. The term y sub I minus y bar is what we call the total deviation. Next, RSS, the residual sum of squares, also called the error sum of squares, or SSE. Why not ESS? I don't know, it's just a convention. RSS equals the sum of y sub I minus y hat sub I quantity squared. This captures the variation not explained by the model. The term y sub I minus y hat sub I is the unexplained deviation, or simply the residual. And finally, the regression sum of squares, which measures the variation explained by the model. It equals the sum of y hat sub I minus y bar quantity squared. This is the part of the variation that the model captures. The term y hat sub I minus y bar is the explained deviation. Here is the key relationship that ties everything together. Total variation equals unexplained variation plus explained variation. Or, in terms of formulas, TSS equals RSS plus regression sum of squares. So what does r squared actually tell us? When r squared equals 0, the model explains none of the variation in y. All the variation is unexplained noise. When r squared equals 1, the model explains all of the variation. Every data point sits exactly on the regression line. And in general, a higher r squared means a better fit. However, it is important to note a limitation of r squared. The r squared value will always increase as you add more predictor variables to the model, even when those variables are only weakly related to the outcome. This can result in overfitting, where the model captures noise instead of meaningful relationships. To address this issue, the adjusted r squared statistic can be used. Adjusted r squared incorporates a penalty for adding extraneous, non-informative variables. We'll cover the formula for adjusted r squared in another video. Let's compare RSE and R-squared side by side. RSE measures the average deviation from predicted values and estimates the standard deviation of the error term. It's in the same units as Y, and lower is better. R-squared, on the other hand, measures the proportion of total variation explained by the model. It's dimensionless, ranges from 0 to 1, and higher is better. Although both are useful for assessing goodness of fit, R-squared is often more intuitive because it is a dimensionless proportion. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.